All right, hello everyone out there. Hope you're having a great day. Today, welcome to my channel. My name is Thomas. I do educational videos on many different subjects. Right now, we are working on getting through this book called Beyond Space and Time from Dewey B. Larson. This is his final book that came out in 1995, posthumously. He died back in 1990. And Larson is the guy who developed the reciprocal system of theory back in the uh, early, mid, and late 20th century. And it took him a long time. Um, and we've been working on a unit of his work. This is, I believe, the 26th video on this, and this is the 4th video on his book, Beyond Space and Time. Now, we are looking into chapter 3 and chapter 4 of this book. Basically, if you are just tuning in, you may want to go back and start at least at the beginning of this book, if not all the way at the beginning of the reciprocal system videos. But if you want to just wing it, I'll give you a little bit of help. Larson's the basic gist of Larson's system of theory. It's a theory of everything. It's a system of theory, meaning that if you have the basic postulates, then you can go and you can create your own theoretical universe and plug his system of theory into whatever subject you want. And the basic gist of it, I will just pull up his two postulates, and the first postulate is the physical universe is composed entirely of one component. Now, I'm interrupting, but the physical universe is composed entirely of one component. Back in the ancient times, in the Greek times, all the way up to Einstein, that component was thought to be matter. The universe is composed entirely of matter. Then Einstein comes along with E equals mc squared, and energy equals matter times the speed of light squared. Energy can be converted to matter and vice versa. So Einstein is really saying the physical universe is composed entirely of energy. Well, Larson, shortly after Einstein, comes along and says the physical universe is composed entirely of one component, motion. Okay, so Larson really says that since E equals mc squared, since energy and matter can be converted one to the other, neither one of them can possibly be the component that the universe is composed of. Because there's something that underlies both of them. And so he points really at the c squared part, the motion. The universe is composed entirely of one component, motion. Now, again, as I pointed out, other people have contended that the universe is composed of motion. People like Thomas Hobbes. And but Larson extended the theory by defining motion, unlike his predecessors. And he says the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. So those are really the 3 qualities of motion. They have it has 3 dimensions. It's in discrete units, meaning it's quantized. You can't have half a unit. You can't have a third of a unit. You either have one or you have none. And then once you have one, then you either have 2 or you have 1, but you don't have 1.5. Oh, well, actually, you may have 1.5 because sometimes things are divided by 2, but you won't have 1.53 or something. and with two reciprocal aspects, space and time. That's the important part. So for Larson's system, the universe is made out of motion. Motion is the relationship between space and time. Space and time are, now this is me again, space and time are identical to each other except that they are reciprocals, and they are reciprocals in motion. Motion is any relationship between space and time. So this serves as a great check on science, where Larson basically breaks down all kinds of scientific phenomena and identifies them as relationships between space and time. For example, speed. This is the most basic example. You have speed. The car is moving 10 miles per hour. 10 miles of space in 1 hour of time. That is speed. Speed is space over time. Now, the inverse of that would be time over space. And that is, it took me 3 hours to move that thing 20 feet. Okay, that is energy. Time divided by space is energy. But again, the universe exists in 3 dimensions. So you can have time, for example, time to the 3rd power over space to the 3rd power. And it turns out that that is matter. Matter is time to the 3rd power over space to the 3rd power. Now, let's look at E equals mc squared. Energy, time over space, that we just determined. Energy is time over space. Energy equals matter, time to the 3rd power over space to the 3rd power, times the speed of light squared. Speed equals time over space. So the speed of light squared is time over space times time over space. Space over time times space over time. So space to the 2nd power over time to the 2nd power. And then when you multiply that by the matter, time to the 3rd power over space to the 3rd power, times space to the 2nd power over time to the 2nd power, you get time over space. Energy equals matter times the speed of light squared. So in this particular case, this equation checks out, in terms of units. But you can also use this for other equations, and there are other determinations that Larson made. For example, impulse. Impulse is time to the 2nd power over space. Or acceleration. Acceleration is space over time to the 2nd power. That object falls at 9.8 meters per second squared. And that's, 9.8 meters of space in 1 second of time per time. So space over time to the 2nd power. Force equals time over space to the 2nd power. So anyway, there's equations for each kind of unit in the legacy science system. Okay, now moving to the second fundamental postulate, the physical universe conforms to the relations of ordinary commutative mathematics. Its magnitudes are absolute, and its geometry is Euclidean. Now, again, there's a lot of dispute about this postulate. The people that have come along more recently to update Larson's theory mainly disagree with this, especially in terms of the Euclidean geometry, and have proposed projective geometry, which Euclidean geometry is a subset of projective geometry. So they're really saying that Larson was limited by using this using Euclidean geometry. Euclidean geometry applies in most cases, but not all. And there's a bigger frame that we need to use, that of projective geometry, to cover all of the things. And Larson most likely agreed. He did have a comment in one interview where he did say that there are other geometries out there that I could have used, but it's actually more difficult to figure, to work with them, that it's even worth. So I'm using the Euclidean geometry almost just to be simple, but I don't know that is really going to stand the test of time. We need to have it accurate. And Larson also has said, as I've said on here, that the reciprocal system, so he starts with these postulates, and then he goes step by step. If this, then that. If this, then that. If this, then that. And that's the deductive development of the reciprocal system. And we talked about his paper that he gave back in 1986 about that. There's about 15 episodes on that. And, he did say that that theory itself, his theory incorporates all of science. 90% of legacy science fits into his theory when he goes, if this, then that, if this, then that. Those that's, whatever comes out of that theory is pointing at a certain identity. And then he has to match up that identity with whatever legacy science has already come up with, or if they have come up with something that matches the quality of that. And he says that 90% of legacy science fits right into his theory. But his theory sheds light on legacy science in regard to the very small, the very fast, and the very large, and the very slow. So those are around the margins, and that is actually where the projective geometry comes in, and the other geometries that are part of this geometrical cascade that Euclidean geometry is a part of. But Euclidean geometry really only applies, in the same sense that the Newtonian universe is built upon. But once you start getting into the very slow, the very fast, the very big, and the very small, then you start needing some of these other geometries. So I think Larson probably was a little bit wrong about that. Now, we were here in the, this is moving slow, but I'm just trying to, get you to the point where you're understanding where Larson's coming from. So he's using this inductive process. Once he started making these scientific measurements about various things and observations about various things, and he uses an inductive process to go from the specific to the general in order to develop the theory. Now he knows that the specific to the general is not as reliable as going from the general to the specific. You need to use the inductive process going from specific to general, but you also then have to be able to verify that. So, he's saying, well, in this specific case, in this specific case, that. So I'm going to say that it's a general thing. It's a recourse to, as he says, a recourse to probability. It's like, well, if this specific thing is true, and this specific thing is true, and this specific thing is true, then it's very likely that it's a general situation, but that it still needs to be verified. But he uses that to develop the theory until he gets the postulates, and then once he gets the postulates, then he flips it around and goes with the deductive phase, where he's saying, if this, then that. So the deductive phase is general to specific. So I've got these two generalized postulates. Now I can apply it to the specifics of the universe. And he creates this whole theoretical universe that it just happens to match up very well with the actual universe, or at least the legacy science universe of legacy science. Now, here, he's in his last book, he's attempting to apply the reciprocal system not only to scientific matters, but to metaphysical matters. Things having to do with the liberal arts, philosophy, religion, ethics, um, uh, all the subjects of philosophy, psychology. These are what he's attempting to extend this theory. So when he's extending the theory, he basically has to go back again to the inductive reasoning, and that's kind of where we catch him here. I know that I've taken a long time to explain this, but that's where he's at then. And so he's explaining how he starts to reuse the inductive reasoning, and he starts to really kind of try to defend the various processes of inductive reasoning that he's using, including analogy and extrapolation. So he's saying, now again, in Einstein's universe, the speed of light is the maximum speed of the universe. In Larson's universe, the speed of light is the midpoint of the universe, and half the universe is moving slower than the speed of light. This is the physical universe, and half the universe is moving faster than the speed of light. This is the metaphysical, or we call it the cosmic universe. He calls this the material and physical universe. But he's saying that, using this extrapolation, because of the reciprocal system, reciprocal relationship between space and time, he's saying that whatever is a reality in the physical universe is actually also true in the metaphysical universe or in the cosmic universe, only that you have to just invert space and time. You substitute time in for space. So he's saying that if we can determine what's going on in the physical universe through extrapolation, specific to general, we also can determine what's going on in the cosmic universe. And so that is, that's where he turns around and goes back to the inductive reasoning in order to determine how the metaphysical universe is operating. So we say, saying inductive reasoning, a special type of existence that in the physical universe, existence in general. Deductive process is complete in itself, and if sound reasoning is applied to valid premises, the process of deductive reasoning arrives at conclusions that are physically certain. Induction, on the other hand, is a probability. Induction is therefore an incomplete process, and the inductive conclusions must be verified. Thus, the equivalent of deduction is not induction alone, but induction plus verification. Now he says the basic process is simple enumeration. If the number of observed units is immense, as is often the case, the probability is so great that it is equivalent to physical certainty without any further verification. So if you have, a million specific examples, like each time I throw, an apple across the room, it falls to the ground. I did it a million times. Therefore, I can make the generalization that is some kind of law, like something goes toward the ground, and he says that becomes a physical certainty just on the basis of probability, and you don't have to do the verification. Like if you have enough numbers, if you do it enough times, enough specific cases, then it's equivalent to a physical certainty without any verification. A somewhat less reliable form of extrapolation, still low is extrapolation, still lower degree of probability is analogy. Since a certain entity A has property X, some entity B that resembles A in certain respects also has property X. So, you know, you can say that by analogy. Okay, well, I threw the apple and it fell to the ground, or, and then you come up with an analogy and you say, well, if it works for an apple, it probably works for an orange. I threw the orange and it also fell to the ground. So, that's an analogy that is like, okay, I tried it with one thing and I tried it with something else that resembles that thing and it worked too. But then you can also say, well, so I figured that anything round would work. And so I tried it with this helium balloon and I did it and it didn't work. So that analogy is less reliable, than the first analogy, and it's less reliable than a straight inductive process. Okay, still lower, and then he talks about concomitant variations in which a connection between X and Y is inferred from the fact that the analysis shows that factors which cause a change in X also cause a change of a related nature in Y. Okay, now, so today all we really did get through is this inductive reasoning, but it's an important thing. And so we're still here in chapter 3. We're going to get into more on Larson the next time, on where he's going with this and how he's applying it. All right, have a great day. See you later.